Good evening, everyone. I know it's a little strange. For the first time ever, Foundations of Algorithms is meeting at night. And I'm very glad to see how many of you are here. I also hope you will enjoy the pizza that is soon to be ordered, on its way. Now, today is one of my favorite days because the historical figure that we're talking about is someone pretty special to the history of computing. And in fact, someone that many of you may already have heard of. This is Alan Matheson Turing, who was born in 1912 and passed away at a young age in 1954. He formalized the concept of algorithms and was also known for the idea of Turing machines, which was really a mathematical way of describing the entire notion of computation. He also came up with the Turing test, which was an early attempt to try and figure out what an artificial intelligence might actually look like. And on top of all of that, he was also one of the key figures behind the breaking of the Enigma cipher, the German code machine that we spoke about in our very first lecture. Now, a very important fact about Alan Turing, for historical reasons, is the fact that he was a gay man. And in 1952, it was still criminal to be homosexual in the UK. And so in 1952, he was prosecuted for homosexual acts and was chemically castrated as an alternative to going to prison. He died June 7th, 1954, at age 41 from cyanide poisoning. This was long suspected to be a suicide, although we don't really know, and it was only a few years ago when he was formally pardoned for the UK. And despite being one of the fathers of computing and of our entire field, it took this long for us to really recognize him properly. Now, the other thing about Turing is you'll find his name across many parts of computing, and in particular, the Nobel Prize in Computer Science is the Turing Award. That is the equivalent of the Nobel Prize for our field. And hopefully a little later in semester, we might talk a bit about some of the Turing Award winners. So here is a figure that if you know no one else from the entire semester, someone who I want you to remember. And as of 2021, he now appears on the £50 note in the UK with the words, "This is only a foretaste of what is to come and only the shadow of what is going to be," presaging the digital era in which we are now living. So, taking us to where we left off, we had started to develop a few different techniques to build up algorithms. And the key one for today, and that we're going to visit probably after the semester break as well, is the ability to do work now to do less work later. This is the idea that if we perform some amount of pre-computation, work ahead of when we actually need the results, and then later on try and actually compute a smaller algorithm, we can save ourselves a lot of effort and save on the asymptotic complexity when we have to do either repeated work or when we have to do work on that data set at a later point in time. So this takes us back a little bit before. I'm going to refresh your memory from a few weeks ago to our question of why bother sorting. So let's take our memories back and think first about comparing sorted search and unsorted search. So I am going to need a volunteer in just a moment, but before then, let's revisit the notion of linear search. So here's the problem. I tell you that somewhere in one of the boxes that I have, and you haven't opened them yet, there is a value x. And a series of boxes in our computer's memory, of course, is just an array, and it's an array of length n. The intuition here that's going to be driving a lot of our talk about efficiency is in the normal case, when this is the way I presented the problem, you're going to, in the worst case, have to look through all the elements to figure out if it's in there or not. Maybe you'll be able to stop partway, but without opening the boxes, you don't know where to begin, you don't know when to end. So here is a more pseudocode description of linear search, and let's spend a minute going through it. So set a variable I to be 0, then while I is smaller than the size of the array and the current item that we're looking at is not the item that we wish to find, increment through the array. Then when I gets to the very end, if I has indeed gotten to the very end, return not found. If our loop is terminated early, that means that we have found the item we were looking for. We've found X. And so return I, the index where our loop stopped. So I'm going to go ahead and do linear search for Bayswater Mazda. Now let me get to the start of the listings. AA back open locksmiths, AABA modem speed problems, AAA it's Jimmy K's sound extremist. That one sounds fun. AAA resi check, AAA tree man, AA sprint driving school, act of pleasure, adorable babe, adult, Algeo Australia. Wow, there were some interesting entries in there. But you know, I'm getting bored. We're going to be here a really long time before I get to Bayswater Mazda. Now, we'll come back to this in a moment, but in the algorithm that I have here, if there are 161 pages in the book, how many pages am I going to look at using the algorithm that I've got up there? And Tammy, you can answer this one. Let's pass this back. It'll turn green in a moment.
159.
Why 139?
59.
So there are 100 and, what did I say, 161? There are 161 pages in the book. So how many pages am I going to have to look at to finish the algorithm?
160.
Yeah, why?
Because they're doing linear research.
So it's not just because I'm doing linear search. We'll talk about an optimization in a minute. But specifically, this loop says to go through the entire thing until I find the item. And if my item is not found, I'm going to have to look through the entire thing. So in the worst case, I'm going to have gone through all 161 pages before I actually know that I can terminate. So this is probably not the best algorithm, and we'll come back to it in a minute. In fact, we've already seen this semester a way of doing it better, but I want to talk about it again. So what we want to do, aside from analyzing the runtime though, we also want to prove its correctness. Now, I gave you a bit of a sketch of how we know it before, and in fact, it should be obvious to many of you that this algorithm works. But we need to prove it. So how are we going to do it? Well, this is just like a mathematical proof. There's no obvious way that I can just tell you, well, if you have an algorithm, this is always the proof for the algorithm. It's going to be dependent on a little bit of insight. But there are a couple of steps, and we'll go over this a few times, that you can use to try and figure out how to generate a proof. And we'll do one particular style of proof in this class and over the course of this semester. And hopefully, as you grow in computer science, you'll learn other proof types that we can use to prove the correctness of our program. So this type of proof is known as an invariant-based proof. What we want to do is we want to find a statement, a mathematical statement, that is going to be true pretty much all of the time for our program. And we have to pick this statement carefully, and picking this statement is one of the bits of insight, the bits of creativity that actually makes it a proof rather than just something that's obvious. But there are some ways for us to go about ascertaining what this thing that's always true about this program is. So for the time being, we're just going to start with, I will show you a useful invariant for proving the correctness of this one. And then in our next problem, we'll try and work backwards and see, can we figure out what that insight is? So here is the written, slightly formal form of the invariant for linear search that I will use to prove its correctness. Now you'll notice the triple bar symbol here. You'll notice some formal things here. The notation looks a little scary, but the translation is actually relatively simple. The 3 bars here means this is the definition of P. I'm just calling this P, this is my proposition, and this is what I set it to be by definition. So the definition of P is the truth of this the definition of P is this statement. Is it true that I is between 0 and n inclusive? And also true that X, the item that we're looking for, is not in between the 0th element of the array and the last element of the array that we looked at. So not the element of the array that we're up to, because then it would be from 0 to I. This is everything that we've already passed. What this is effectively saying is if I am halfway through the book, it should be the case that the thing that I'm looking for is not in the part of the book that I have already looked at. It could be on the page that I'm about to look at, but it should not be in the set of things that I've already looked at. So we're at I in the array, and we haven't found X in the prior elements, is what this invariant is saying. So now we can take our linear search algorithm and rewrite it. Okay, so the first thing to note here is the use of a new keyword. You've probably never seen this word assert before, unless you've programmed in a similar programming language. And this word does exist in C. Now I'm using it here in pseudocode, but we'll pretty soon see how you can actually use it in your own program to turn your program into a proof of its own correctness. And strategically, what we want to do is we want to say that at all relevant points in the program, our invariant is going to hold true. So this is a statement that we want to be true across the entire program. And then at the end, we want to think carefully about what the result of our program should be. So our program really has two possible outcomes for linear search. Outcome one, Tammy, what's the good outcome if I'm searching for something in my phone book?
Found?
Yep, that's the good outcome. I found it. What's the bad outcome?
Not found.
Not found it. Perfect. So here I'm going to construct a formal way of writing both of those things. So let's jump first to the case where we have found it. That's this bottom case over here. So I'm saying first, P is still true. My index I is within the bounds of the array. Okay, that should be obvious. And then if I is, so P is still within the bounds of the array, and the item that I'm looking for was not in all the prior items of the array. The first thing we want to state is that the item is not in the pages we've looked at so far, and we're still within the bounds of the array in terms of our value for I. Okay. The next part of our compound statement is itself a compound statement. So it is the case that either I is greater than equal to n. Why? Because if I was not greater to or equal to n, then we wouldn't be outside our loop, unless we had terminated the loop early because the current item that we're looking at is the one we're searching for. Those are the only two ways to exit the loop. You can exit the loop because you're at the end of the array, or you can exit the loop because you have found the item you're looking for. So that's our or statement here. One of those two things must be true. Okay. So if I is not greater than or equal to n, so if we're not at the end of the array, that means that we know that this statement over here is definitely false. So the reason the loop ended is not because we were going outside of the array. So if the loop has ended, we know that the value of I is within the bounds of the loop, and the item is not in the things previously, then there's only one conclusion left. The current item that we're looking at must be the one that we were looking for all along. I'll say that one more time. Why? Well, we know that we're in the array, that I is within the array, because that's part of our statement P. Okay? We also know that the loop can only end one of two ways. It can end because we're looking at the correct item, or it can end because we've gone past the end of the array. And I'll give you one additional fact over here. We're not at the end of the array, which leaves us one conclusion. We must be looking at the item we're searching for. So that's our first case over here. Now let's look at the other case. It begins the same way. So where the item that we want is not in the pages prior, and we are still within the bounds of the array loop. But in this case, we know that I is greater than or equal to n, which means we've reached the end, which leaves us only one conclusion, that because we're now going outside the end of the array, and we haven't stopped early. The fact that we haven't stopped early is evidence that the thing that we were looking for is not in there at all. Now, in order for this to make sense, we must have been sure that P was true all along. So now we actually have to check P inside the loop as well. So inside the loop, we're asserting that P is true. So I, our index, is between 0 and n inclusive. How do we know that's true? Well, our loop bounds combined with our setting of I to 0 at the start guarantee it. So I was never less than 0, so we know that we were in that sense correct, that I was definitely greater than 0. And we know that, that it is less than n, because otherwise we would be outside the loop already. The loop would have terminated. And we also know that I is not equal to, that the ith element, so the current element we're looking at, is not the correct one because that is the other loop termination condition. Then what we do, we increment I and check, is it still the case that I is between 0 and n? It must be the case because the previous line had I is strictly less than n, and our statement P has I is less than equal to n. So adding 1 to it can't possibly violate that condition. So you add this all up, and what we've essentially said is that at every stage of our program, our invariant P is true. And then combining our invariant with these two cases and making sure that, by way of proof, that P is never violated, we've proven the correctness of the overall program. Because there's no way to escape each of these cases. You're either in one case or you're in the other case. And so these statements as a whole form a proof that linear search, that our algorithm for linear search is indeed correct. Now, this looks a little different to many of the types of proofs that you have written in perhaps maths classes, but they are in a deep formal sense actually equivalent. There is a very, very famous result in computer science called the Curry-Howard theorem, which states that every program is a proof and every proof is a program. And we're not going to have time to really go into the depths of that. That's something that you might be able to access in graduate studies in computer science. But I think it is one of the most beautiful things about computer science is this deep connection between proofs and between programs. So if we want to prove correctness of a program, one powerful tool that we have is to use invariants. And indeed, Edmund Dijkstra, who is one of the heroes of practical programming and as well a computer science professor, wrote a whole paper on how to use invariants as a way to actually construct correct programs as you're going along. And this is incredibly powerful. So that takes us to the end of our proof of correctness for linear search. But now we want to talk a little bit about the runtime.
We need people for pizzas. 20 of them. We need people like to help guys.
We need 3 people for pizzas?
Yeah, a few more people. A few of us are going.
Okay, does anyone want to go on a pizza run and feel they already know this stuff? You can watch it on YouTube later. You are the heroes of the class. We'll give you a round of applause when you come back. Guys ready? You're giving it back.
Yeah.
We're going to take this one out of the lecture capture. Oh, you didn't get a bottle of water? Pick up a bottle of water on the way. The question is, what are they going to buy with my credit card while they're out of the room?
Is that your actual?
That's my actual credit card. I just let 4 undergraduates run away with my credit card. If anyone has their numbers, you can text them a bunch of things to buy. Okay, so we're now ready to talk about the runtime of linear search. Now, it seems a little silly to ask about linear search. After all, you guys know enough to know that it's O of n. Okay, let's break that down a little bit more. So we actually have multiple cases in which we could evaluate the runtime based on the distribution of data that we're receiving for linear search. So let's say I am looking for the number 5 in the array, and the order of the array is 5, 12, 13, 24. What is the runtime of my algorithm? Zero? Got a Lily? 1. So in the number of comparisons that I have to do, I'm only going to have to do one comparison. But I kind of buried the lead here a bit because it's not really reasonable to say what is the runtime of the program as a whole. And like we're used to talking about big O and general cases when I've given you a very, very specific instance. But what this does illustrate is the best case runtime of linear search. So in the best case, the generic best case is where someone has gone and put ahead of time the very item that you're looking for in the first place, and then our algorithm is always O of 1. But that's not really a very good description of linear search, is it? So the case that we are going to care about a lot as computer scientists is the average case. And one way we can think about this is if the distribution of data was random, how long would our algorithm take to run? And so in the case of linear search, you can think of this as I'm randomizing the position within the array at which the item that I'm looking for could be found. And actually computing that is not always as straightforward as it seems. But in this case, I will tell you that it is still O of n for linear search. And then the worst case is a very safe runtime to talk about, but it might not always be the most realistic because many things in the world aren't constructed to always give you the worst case over and over and over. You're often better off building systems that perform well in the average case, but still being aware of what the worst case is. And for linear search, what is the worst case? If I'm looking for the number 5, where might the number 5 be? Well, it might not be in there, which is the truly worst case, but if it's in there, it might be the very last item, in which case we're guaranteed to run n steps every single time we run. So we generally hope for the best, we plan for the worst, or at least the average case. And this is true in system construction. So when you go out into the world and have forgotten all about formal analysis of big O, this is one of the skills that actually still will remain very useful and very salient. Because when you're analyzing the practical performance of a program, you might do something called profiling, which means to test it in a variety of circumstances and figure out how long it takes to run. And recalling these patterns of behavior might be a really effective way. Now, we should plan for the worst as well, because sometimes our data is not best case, it's not random, it might be adversarial. Someone might intentionally try and construct inputs to your system that get it to behave in the worst case. And this is one useful thing if you are a malicious individual on the internet trying to bring down a website. You're going to look for perhaps flaws in the algorithms that the website runs in order to get it to consume cycles and overwhelm it and bring it down. So can we do better? So this is where I need a volunteer. Now, Nicole, because it's her anniversary, is going to come down to the front and help me. And a very happy anniversary. Okay, I'm looking for the maternal healthcare unit here. So what should I do? Should I start at the start?
Yeah, I think so.
Okay, use the microphone and tell the crowd.
Yeah.
Okay, I'm going to start at the start.
Yeah.
This is where A's begin. So AAA is Jimmy Sound Extremist, AAA Resi Check, AA Tree Man, AA Sprint Driving School,
Maybe it's too long.
Okay, too long?
Yeah.
What should I do?
Maybe to decide like which one we should start, like the first one.
Okay, so let's assume we don't really know the distribution of things in here.
Yeah.
Where should I go?
Distribution. It should start with T.
Yeah, let's say I don't know where things are, but I'm looking for maternity in here.
Maternity.
Yeah, it starts with an M.
Start with the M. A, B, C, D. Yeah.
I do that too.
Yeah. Maybe near to the half. So we can start at the half.
Going half seems right. So I see Nick and Nugri. So N-I and N-U. Which half is it in?
Sorry, can you repeat that?
No worries. In the left half or the right half?
Maybe left half.
The left half?
Yeah, because it starts with the M, right?
Yeah. So I probably don't need this half of the book
Yeah.
to look for maternity, do I?
Ignore them.
Ignore
Just
it?
throw them.
Okay.
Oh my god.
Okay, I still have to find maternity.
Yeah.
So now what should I do?
Okay, so it starts from A to N, so like just half of it.
Okay, half of it. I have FO and FU.
So FU, the last.
FU?
Yeah.
Do I need this half?
No, but maybe not.
Whoa! Students beware!
Boom.
Okay, now what do I do?
Half of it.
This is becoming harder.
Yeah.
Okay, let's try halfway. I have LO and MC, and I'm looking for MA.
MA, the previous one. So
Okay,
ignore the last.
goodbye. And if I look at this page, I'm on MA.
MA, I think it's near to the MC, right? So
So-
maybe we can.
On the right page, thank you very much. And here is pizza. Can we have a big round of applause for Nicole and Tintin? Let's take a short pizza break, actually, for everyone to get some pizza. Thank you. Welcome back, everyone. We're now going to talk a bit about how to do the same thing we did for linear search, but to do for that procedure we just saw live, which we call binary search. Why binary? Binary is 2, and what we were doing each time was halving the size of our problem. So you remember what I would do there is I would go to halfway, look at which side contained the solution to my problem, and I would throw away the other half, essentially halving the amount of work that it was possible for me to do. So with repeated halving, the number of steps that it takes me is actually logarithmic, log of base 2. And we'll see in a little more detail why that's true in a couple of minutes. So up on screen now, I have the algorithm for binary search written in that more formal notation. But just like we did with linear search, the actual conceptual ideas here are not very difficult, even while the notation might appear to be intimidating. And one of the challenges as you grow in maths and computer science is to find a way to calm down when you see a bit of scary notation and translate into something that's far more approachable and far more intuitive. Because most of the time with algorithms, there is an insight hidden there. And once you understand the insight, the entire problem becomes much easier. So let's look at how this algorithm actually works. So what we start off by doing, and this is a pattern we will repeat later in today's lecture, we start off by showing with 2 variables where the possible solution lies. So at the very start of the problem, now I no longer have my book to demonstrate live with you, but at the very start of the problem, our answer could lie anywhere between the beginning and the end. So let's call this side low and this side high. And high we're going to set to n, where n is the number of possible pages in my book, and low is the very start of the book. And what I'm going to do is I'm going to move where the possible program, I'm going to move where I think the answer could be by moving my variables to indicate which parts of the problem I've eliminated. So anything that is higher than high is not where the solution could be found, or anything that is lower than low. So let's say that I start my algorithm, and the first time I look at the middle, I see that the item I'm looking for is in the lower half. Which of the 2 variables should I move? I move high, down to the middle, and now everything from the middle upwards, I'm going to ignore. Now let's say I look in the middle of these 2 hands again, and I see, oh, now it's in the higher half of the 2. Which of my 2 variables do I move? Now I move low, up to the middle. And now I know that everything on that side no longer could possibly have the solution. And I repeat this process again, halving and halving, until there's only one possible place left to look. And if I look in that last possible place and the thing I'm looking for is not there, what do I know? It is not in there. And so that's exactly what my code is doing here. So while low is less than high, so while my hands have not like crossed each other, which would make no sense from the continual running of this algorithm. So while my hands are in the right place relative to each other, figure out the midpoint and call it M. If X is in the lower half, move high and set it to what that midpoint was. Otherwise, if X is in the higher half, move low to that midpoint again. Keep doing this again and again until you're in this third condition. Now, this third condition, if X is not in the higher half and X is not in the lower half, and you know that X is actually in there, whereas the only place that X could be, right in the middle. Thank you, Devansh. And so in that case, we can return M. Otherwise, we can return not found. Now, you'll notice here that this is actually quite sensitive to off by one errors. And this is one of the most common types of programming errors that you might find. So if you write these conditions slightly wrong, you might end up in a scenario in which case you've calculated that midpoint slightly wrong, and now you have overlapping, or a case where you might not be looking at a particular element at all, and your algorithm will fail. And this is one of the reasons why the kind of invariant-based programming that we were trying out before is actually really useful, because it allows you to write your code in a way such that you can get a much stronger guarantee that the particular way you've written your code is correct and that you have not actually introduced one of these off-by-one errors. So now, in order to do our proof of correctness for this, we need to find our invariant and our correct post condition. Now, you'll remember from linear search, our post condition were those two special statements that we had at the end. Either we're in this case or we're in that case. And if this condition is true, then we know that answer coming from that branch is correct. Or if this condition is true, then we know that the answer that came from that branch is correct. So what we're looking for is our post conditions. So how do we go about in this looking for the right post condition? Remember, this is a creative process, so this is not something that I can actually instruct you on, and then you go and do it 6 times, and then when you do it the 7th time, you do exactly the same thing. And this is one of the things that actually makes a graduate algorithms course quite hard, is because they get you to do some of these proofs, and they get you to do it on the basis that you've developed a feel for where the right solution might be, without actually having given you an exemplar of the same type earlier on, or of the same narrow type. They give you something of the same broad type. It's hard, and it's also a lot of fun. I got like 40% on my graduate algorithms exam, and that was a solid A. But that's how these exams kind of work, because they get you to make creative leaps. It's a challenge. It's like the Putnam math competition, where if you solve even one of the problems, you're a world-class high school mathematician. So finding proofs can be a little bit like that. But to take us a bit more back to earth, what are some concrete things we can do in order to figure out the right post condition? So here are 3 of them. 3 of them. So one is, start by thinking, when the function ends, what does the calling function expect? What are the different valid things that my function could answer? Is it either a 0 or a 1, or is this should return an index, and that index should be in a specified range? Is it an ordering of things that should be the output? What is the output that is considered valid? Then, if there are multiple different cases, like found or not found, or within the array or not there at all, split the output into those cases and figure out what are the different possible conditions under which those would be true. And then come up with a sample post condition and make it strong enough so that you're very confident that you can rule out being in the other case or getting a wrong answer by the post condition that you have written down. So one other way of thinking about this is, in order to complete the proof, you need your post condition, your invariant, and kind of a way that the algorithm will make progress each time. So as the loop runs, you're getting closer and closer to your post condition being true. And what's non-obvious often in these proofs is not the postcondition itself, because you can be a little more aware of what you expect. It's actually finding out how to connect that postcondition to the progress that the algorithm is making. So it's often those halfway statements that can be really tricky. You have to notice how to connect the final goal to the ongoing running of the algorithm. So let's actually do this for binary search. And I will tell you in advance, I'm not going to make you invent any of these for your first year algorithms class. I think it's helpful to have seen it and to be able to replicate one that you've already seen. But I won't be giving you a novel algorithm and saying like, here, prove its correctness from scratch. It's probably a little too hard. So up on screen, I'm going to show you the invariant for binary search. So here we have define our invariant. Let's call it P again. And we're going to write it as follows. So the first thing is that low should always be less than or equal to high, because otherwise my hands have crossed over. So low should always be less than or equal to high. And both of those should be less than or equal to n, where n is one step outside of the array. So if the array indices go from 0 to n minus 1, n is one step outside of that. And also remember that going back to the linear search algorithm, it kind of hinged on that n being one step outside a little. So if you missed that before, that's a potential place to get tripped up. So we have our ordering of our hands. We have low is over here, high is over here, and there is the end of our array. Next up, we want to say that anything below low, the item we're looking for, x is not in there. And anything above high, x is not in there. And that's what our two statements on the other side of our invariant are. And having talked about binary search a lot now, this kind of makes intuitive sense as an invariant. If this were not true, our program would not work. If it's not true at any point in our program's running, we have messed up somehow. So in order to build our algorithm overall, our invariant has to start off true. So here we have this with our initialization. So set low to 0 and high to n. And at this point, we know that our invariant's true because we haven't, right now, there's nothing inside those bounds. So there's nothing lower than low, there's nothing higher than high, so we know that x isn't there. And we know by construction that we've set them up so that they're both low is less than high and high is less than n. Okay, now we have our loop. While low is less than high, so if this loop condition holds, then we know that P is still going to hold, and low is less than high because that's in our loop statement. Seems trivial, but we're going to write it down just so we can carry the proof through. Now construct M, which is that midpoint, and now assert P. So we know nothing has changed so far because we haven't moved low and high, and so we couldn't possibly have violated it. And now by construction, M is greater than or equal to low and less than high. Now you'll notice here that our midpoint calculation is using integer division because we're writing this algorithm as if we're going to implement it in C. So this means if M was like 6.5, if M would have been 6.5, it's going to be truncated down to 6 because of the way that C treats integers. And this is why we have greater than or equal to low, but definitely less than high. Now we have our two branches. So this is where x is less than the midpoint. The value we're looking for is in the lower half. So first thing we can do is we can assert P as well. We still haven't moved our hands around, so it's still true. And now we know that x is less than everything to the right of the midpoint. And that's what that statement there is saying. X is definitely less than everything from the midpoint up. Okay, true again. Seem to be going well so far. And now, here's the slightly trickier step. We move high to the midpoint. And now that we've moved high down, we need to check that P is still true again. Only now P isn't as trivially true. We still need to guarantee ourselves that low is less than high, that high is less, and that high is less than n. Now we know that m is less than n, so we've only made high smaller, which means we're definitely sure that high has only gotten smaller, it hasn't gotten bigger than n. And we also know that low is less than high because we're guaranteed that m was bigger than or equal to m. That's low was less than or equal to m. So by setting high to m, we know that we haven't invalidated that ordering property. Now we do the same for the other side. We know that p is true still. And in this case, x is bigger than everything from the midpoint down. And because x is bigger than everything from the midpoint down, that retains our guarantee. Now, I'm not going to belabor the point there because it's the exact same argument as we did for the upper half. And now we have our third branch. In our else case, we know it's not the case that x is less than the element at index m. We know that it is not more than the element at index m. So it must be equal. That's the only possible alternative. And so in this branch, we're going to assert the following compound statement. So p, because we haven't moved our hands around, and x is not less than m, x is not bigger than m, 3 dots, mathematical notation for therefore. Therefore, x must be exactly equal to m and return m. Now, the only condition we've got left is where the loop has exited after finishing its entire run through. And the only time that this happens is when low and high have converged. And so in this case, we can say p, and low is now bigger than or equal to high. Why can we say that it's bigger than or equal to high? Because that's the only case in which this loop terminates, when low is going to be exactly equal to high. And that allows us to return not found. This is our other case, our other post condition. Assert means the following is true, and if it is not true, then the program should catastrophically end at this point and throw an error. Because something has gone terribly, terribly wrong, and this statement should never not be true. And so the way it actually works in C is if you write assert, and it turns out to be false, the whole program just dies immediately. And so in the case here, it's an assertion that you're making. Given that this is not actually running code, it's a representation of code. So saying it must be the case that. It's a statement that you believe to be true and that you have a proof of is true in this case. Moving on a little, we can now talk about binary search's efficiency. And really visually, we had a very tangible sense of binary search's efficiency because we could physically see me throwing away half the problem at each step. And so really the key question here is how many times can you throw away half of a problem before you get to the problem being of size 1 and you only have one possible answer for the problem? So we can write this out in terms of a recursion relationship, which is another way of writing out the runtime of a program which has recursion in it. Now, in this instance, you'll notice that I actually wrote out the program in an iterative way. But binary search can easily be written out in a recursive way as well instead of the loop. What it would be is when you, instead of having low and high pointers, what you do is you give half of the problem, whichever half the answer is in, to another copy of binary search. And you say, hey, binary search, look at that smaller half of the problem. And that binary search will throw away half the problem, and it can speak to another copy of binary search. And that copy of binary search will look at half the problem again, and half the problem again, and half the problem again until you get to 1. Now, at each step, we know that we have a linear number of steps to do. All we're doing is looking at the midpoint and then making one key decision: which half do we throw away? And that is going to take a constant number of steps. So that is C steps. I shouldn't say linear, I should say it is going to take a constant number of steps. So for each call to a recursive version of binary search, we're going to do that constant number of steps plus half of whatever work we had to do at the current stage. So that is our plus T of n on 2. And then we can ask the question, how many halvings will there be? So this is where logarithms come in, but we can easily write this out in a way that avoids us having to think about logarithms because they're often a place where ordinary humans get a little muddled for a little. So let's write out the pattern of halving. So we go from n to n on 2, to n on 2 on 2, to n on 2 on 2 on 2, to n on 2 on 2 on 2 on 2, or I didn't quite say that right, but you get the idea. And eventually we keep doing the halving and we will get back to having only one item, assuming that we're doing integer halving. So the other way we could write that is n on 2, n, and then n on 2, and then n on 2 to the 2, and then on n on 2 to the 3, and so on and so forth, until we get n on 2 to the k. And n on 2 to the k, that's our last step, and that's going to be 1. There is some value k such that when we raise 2 to the k, n on 2 to the k will be 1. So that's giving us our number of halvings I can do. So let's rewrite that a little. N on 2 to the k equals 1. Let's multiply both sides by 2 to the k, and then take the log of both sides of base 2, and this gives us log n equals k. And so we're going to do C operations log n plus 1 times, because this tells us how many times we do the halving, and each time we do the halving, we're going to do C steps. So that's going to give us our runtime over here of O of C log n plus C, which is big O of log n. And there is a nice, relatively simple proof that binary search is big O of log n. Log n is much more slowly growing than n, and so this gives us a huge benefit in efficiency to binary search over linear search, but it required us to have a sorted book. And that is really where a lot of our motivation for thinking about sorting in this class comes from. So now we're going to take a minute and I'm going to tell you about a lovely book that I read that I highly encourage for all of you who have a deeper interest in programming. It's called Programming Pearls by a famous programmer called John Bentley. I've assigned binary search in courses at Bell Labs and IBM, 2 of the foremost labs in the world. Professional programmers had a couple of hours to convert the description of binary search into a program in the language of their choice. High-level pseudocode was fine. At the end of the specified time, almost all the programmers reported that they had correct code for the task. We would then take 30 minutes to examine the code, which the programmers did with test cases. In several classes that I ran with over 100 programmers, the results varied little. 90% of the programmers found bugs in their programs, and I wasn't always convinced of the correctness of the code in which no bugs had been found. I was amazed. Given ample time, only about 10% of professional programmers were able to get this small program right. But they aren't the only ones to find this problem difficult. In the history in section 6.2.1 of Sorting and Searching, Donald Knuth points out that while the first binary search was published in 1946, the first published binary search without bugs would not appear until 1962. And there is a beautiful picture about why some of the tools that we've been learning about how to prove the correctness of your code actually end up being really important in practice. Professional programmers who spend their lives coding cannot write binary search without bugs. And in a slightly personal story, when I was doing my PhD, I had not read Programming Pearls yet, and Matt Blaze, one of my PhD advisors and a famous computer hacker, got all the PhD students together and said, I will give you a free dinner or I'll give you some money if you can write binary search on the whiteboard. Being somewhat egotistical, as all PhD students are, I immediately went over to the whiteboard and thought I had written out a totally correct binary search. I had 4 bugs. And so all of you shouldn't feel bad if you have some bugs in your code as well. It's both natural, but what we're going to try and do is find ways to avoid them. So we're now pretty down with searching, but in order to do our improved search, we're going to need to sort. And you've already seen with Dr. Wang some of the techniques that we can use to sort. But now I think it's time for us to actually use what we've been building up to. We've now learned pointers to actually put them together to build a search algorithm, to build a sorting algorithm in C. So this, finally, in C, is insertion sort. So let's start with a piece that will now look familiar to a number of you. This is our int swap with pointers. And this is going to be the centerpiece of our sorting algorithm, because our sorting algorithm is what we call a comparison sort, and it's going to rely on swapping items around to get them into order. The core idea of insertion sort is to repeatedly take the next item in the array, so go along the array, go through all n items, and as you get to each item, take it and swap it back into the place it should be within the already sorted portion of the data structure. So just like in binary search, we had this rule that everything on that side is not the item I'm looking for, everything on that side is not the item I'm looking for. The way insertion sort is going to work is we're going to have a pointer at the very start when we're thinking about correctness, and slowly over time the sorted portion of the array is going to grow. And so we also have an invariant. Everything on this side is in sorted order, everything on that side may or may not be in sorted order. So that's not actually going to be part of our invariant because we can't say much. But as we go along, for the ith iteration, everything to the left of my pointer should be already in sorted order. That is our goal. And then all we need to do for our correctness proof is make sure that we're continuously making progress and not violating our invariant. Unfortunately, in today's class, I'm not actually going to put those invariants into practice and show you, but that is another example of our technique in action. So here is the entire really central code for insertion sort. It's only a few lines long. So start at the first item, not the 0th item, start at item number 1, and go through all the remaining items in the array. Now, for each of those items, this is where things get a little trickier. So start one item to the left of that outer item that you're looking at. So if you're looking at the first item for the outer loop, the inner loop is going to start at the 0th item. Now we have a loop condition. So j should be greater than or equal to 0, because if we go less than 0, that means we're outside the bounds of the array on the small side. So we don't want to do that. And then what we also want to do is we want to find the correct position into which we should insert the item. And so if we know that all the items on the left hand are inserted, what we want to do is we want to find the point where the item to the, let's say we're going from smallest to largest, if our item is going to be larger than the one on our left, then we want to ensure that it stays to the left. We never want to violate this property that we've accidentally put something small to the right of something big. And so that is what we're doing here. We want to guarantee that the jth item is always going to be bigger than the j plus 1th item. So this is in fact the opposite order. This is where the bigger item is on the left and the smaller item is on the right. So this is sorting from biggest to smallest. And then all we do is go backwards, scanning along to the point at which we should insert our item. So let's say we have the number 9 over here and we're trying to insert it somewhere, and we have 1, 2, 3, 4, 5, 6, 7, 10, 11, 12. What we want to do is we want to scan along. Okay, there's 12, 11, 10, there's 8. And what we want to do is we don't want to put our number 9 past the number 8 on the other side, because then we'll be violating that condition. Because then 8 would be to the right of number 9. So we want to put 9 just in that place where it's to the left of number 10. And so what we want to do, if we're not at that final resting place yet, we're just going to swap things over. And swap things over and over and over until you've swapped it into the right position. So try swapping it into the rightmost position. If that doesn't work, swap it into the next rightmost position, swap it into the next rightmost position, and keep doing those swaps until it's in a place where you know that if you were to do another swap, you would violate that condition. And that is it for insertion sort. It takes a little time to practice it. but it's actually not a particularly hard algorithm. One useful thing to see is now this is the first program that's starting to get a little more sophisticated in terms of abstraction. We have seen a number of these different procedures before. We've seen a number of these different functions. We've seen read next int. We have seen print an array. We have seen int swap. And all of these are getting used as subcomponents of our larger function. Now, this also gives me time to finally talk about some of the mysterious syntax that we have been seeing in our main function. Today is finally the big reveal. So we have two arguments to main, int argc, and then char star argv brackets brackets. So let's start with argc. This one is fairly simple. This is the number of arguments that your program has been given on the command line. Okay, so that's argc. Now let's talk about argv. So let's simplify it for a minute, and I'm going to take away that. If I take away the star, what am I looking at? What type is argv without the star? Now, let's take the microphone out. Let's go over here. What was your name?
Deb.
Deb?
Yep.
Okay, so what type is char argv brackets brackets?
Char.
Is it just a char? What do the two brackets brackets mean? Do you remember? Okay, how do I store multiple items of the same type?
Array.
An array. So this is a declaration of an array. Now, what does a star do to any variable type?
Is it related to pointer?
Yeah, it turns it into a pointer of whatever the type would ordinarily be. So if I go ahead and add a star here, so without the star, what was it again? Remind me.
An array.
An array of what?
Char character.
An array of characters. So with a star, it becomes a pointer to an
Array.
A pointer to an array of
Characters.
Okay, so a pointer to an array of characters. Now, we're going to revisit that once more, probably either at the very end of this lecture or at the very start of next lecture. But what this is going to contain is the set of characters that were handed to our program as arguments on the terminal. And we will talk about how to use those probably in our next lecture. Thank you, Deb. So now we are ready to try and run insertion sort.c. Enter as many as 10 values. So 4, 55, 2, 88, 38, 97. And then I'm going to hit Control D. Before gave me exactly what I typed in. And then after, it is now in order from smallest to largest. So there is insertion sort, not particularly complicated code, but highly effective at its one job. So maybe we're done. We've now got a searching algorithm. We've got a way to make it better by sorting our data, and then we can search over it. But should we actually be using insertion sort for our data? Well, part of that is going to depend on the properties of the algorithm. We've been talking ad infinitum that it's not just about correctness here. It's also about efficiency. So what is the best case for insertion sort? Deb, you've still got the microphone? What is the best case for insertion sort? What order of data would make insertion sort really fast?
If it's already sorted.
If it's already sorted. So in the case where we get 1, 2, 3, 5, 7, 8, 9 as our input, what do you think the runtime of this is?
It's greater than n squared.
So that would be n squared if my algorithm had required me to check all of the earlier ones. But one of the benefits of insertion sort is that it's actually only requiring you to check up until the point at which you know that your invariant couldn't possibly be true anymore. So in this case, 2 is going to check if it needs to swap with 1. Then 3 will only check if it needs to swap with 2. 5 will only check if it needs to swap with 3. 7 will only check with 5. 8 will only check with 7. And 9 will only check with 8. So how many steps is that? Proportional to the number of items in our array?
N.
N. So we're not going to end up with that n squared behavior, fortunately. But the worst case, what's the worst case?
Everything is sorted in reverse order.
Reverse order. So this is exactly the case we were mentioning before. Okay, so let's start with 8. Does 8 need a swap with 9?
Yeah.
Okay, that's one swap. What about 7? Does 7 need a swap with 9, which is now in second place?
Yeah.
Yes. Does it need a swap with 8, which is in first place?
Yep.
Yeah. Now we're going to end up with 5. Does 5 need a swap with 9?
Yeah.
Does 5 need a swap with 8?
Yeah.
Does 5 need a swap with 7?
Yeah.
Okay. And then so on and so forth, and that is going to give us that n squared behavior. Now we come to the tricky question, and this is again one of these problems which is probably a little outside of having you replicate on your own in foundations of algorithms. For many of the algorithms that we're going to look at, figuring out the average case is actually quite hard. And in fact, I learned a whole bunch of interesting proofs when preparing for this class. But I will show you one of them for our insertion sort average case. So, one thing you can do when trying to figure out how many times we will have to compare things is to calculate how many swaps there will need to be. Because we saw in the first case when we had everything in sorted order, we didn't need to do any swaps. And in the second case, when everything was in the reverse order, that was the maximal one. And in fact, every time that a pair of numbers was in the wrong order was a time that we would need to do a swap, because we need to swap them to get them into the correct order. So here, the number of swaps is going to be the number of inversions, the number of times that things are in the wrong order in the array. So we can count the number of inversions as follows. So let's say we have two variables I and j, which are between 1 and n, and create all these fake variables. They're going to be dummy variables is another word for them. And they're just going to tell us our elements for a given I and j, are I and j in the wrong order. So if the second element and the third element are in the wrong order, then x2, 3 would be 1. Because a 1 indicates that they're in the wrong order, and a 0 indicates they're in the right order. And then what we want to do is we want to sum up all the different xij on average for a random distribution. So for each pair of elements, there is a 50% chance of an inversion. And if we count up how many variables there are, so you can do this using your Calc 1 or Calc 2 skills, there are n times n minus 1 on 2 variables, so that's how many combinations of ij there are. So we'd expect, multiplying that by a 1 in 2 chance, that gives us n times n minus 1 on 4 inversions, and multiply that out, that's n squared on 4 minus n on 4, and that is big O of, it says on the board, n squared. So that means our average case runtime is going to be n squared. Now I will say, figuring out this kind of proof with a dummy variable, again, a little tricky. It's here for your edutainment more than anything. So quadratic time is really not very good. Anything with like a squared in it, we're trying to eliminate. Love to get things down to logarithmic time, but that's probably unrealistic for sorting. So can we do better on average than quadratic time, than n squared for sorting? Okay, here we are. This is the moment that many of you, I know at least some of you in the front couple of rows have been waiting for. This is the Quicksort algorithm. And it's called Quicksort because on average, it's going to be quick. And in the real world, it's going to be quick. And so Quicksort actually is one of the sorting algorithms that gets used to some extent. Now, the funny thing is, and you'll see this a little later in semester, there are some things that look like they're Quicksort but aren't, because in realistic sorting scenarios, there are lots of optimizations you can make about which sorting algorithm you use when. So be careful, sometimes things that are labeled or look like Quicksort actually aren't. Okay. So the key intuition behind Quicksort is as follows. So just like we had our insertion sort invariant, which is everything to the left so far is sorted, Quicksort is also going to have its own set of invariants. And more or less what we're going to do is we're going to have some extra pointers that segment our array into three parts. We're going to have a part that is everything lower than some value, a part that is everything higher than some value, and a part that is everything equal to that value. And that value we're going to call the pivot. We're going to choose our pivot from one of the values in the array. And that choice is going to be relevant later to the actual performance of our algorithm. But from the perspective of figuring out something that works, we can choose any of the values. And our goal is going to be just to divide our array into three parts. A part that is bigger, a part that is smaller, and a part that is the same in the middle. So all the bigger parts should be on the right, all the smaller parts should be in the left, all the parts that are the same are in the middle. Now, of course, if you want to reverse the sorting order, you can do that. So all the bigger parts are on the left, all the smaller parts are on the right, but that's really a smaller detail here. And then we're going to just repeat this process. So take the part that's smaller than your pivot and pick a new pivot and do that same arrangement of three segments. Everything smaller, everything bigger, everything the same. Now go to the smaller part of that and arrange it again. Everything smaller, everything bigger, everything the same. And so this is going to look like a recursive algorithm. Now, you don't have to use recursion. There are ways of writing Quicksort in iterative fashion, but Quicksort for this in particular is probably the most natural way of understanding it. So let's actually try out this algorithm on a sample data set. So here I have a sample array, and what we're going to do repeatedly is just this whole arranging set of steps. So picking a pivot, and then choosing everything, arranging everything smaller than it on one side, everything bigger than it on another side, and everything equal to it. So in this case, just to keep life simple, I'm going to always choose the leftmost item as the pivot. So let's make this the pivot. Now what I'm going to do is go through the items one by one and figure out, are they going to be on the smaller side or are they going to be on the larger side? What's your name?
Melvin.
Melvin. Okay, Melvin's going to help us out with this one. So, Melvin, is 16 in the smaller part or the larger part? So our pivot is 26. 26 is going to be our central kind of focus. Is 16 smaller or greater?
Smaller.
Smaller. Okay, so this is going to be in the smaller part. So green is going to be smaller. 19, smaller or larger part?
Smaller.
Smaller. 12?
Pretty sure it's smaller.
74.
Bigger.
Okay. 27?
Bigger.
38?
Bigger.
26? So how many parts did I say we were dividing this up into?
2?
3 parts.
3.
Everything bigger, everything smaller, and everything that is
Equal.
equal. This is going to go in our middle part. And then 18,
Smaller.
smaller. Oop, I need my green back. And 89,
Bigger.
bigger. So there we have that right there. And I'm going to move everything smaller into the left half, everything the same into the middle, and everything larger to the right. Let me move this out of the way so it's hidden. Ooh. And we're going to call this step the partition step. Partition means to arrange in a particular way, to divide up, and so we are going to partition our array into these 3 chunks. Okay, now we're going to repeat this process again. Okay, Melvin, let's take a look at this subarray right here, and we're going to choose a new pivot, 16. So what do I do now?
Make 19 in the bigger side and 12 the small side.
So 19 is bigger, 12 is smaller. And what goes in the middle?
16.
16. That's exactly what I've done here. I've ignored the other elements in the array, and for now, I'm just looking at this subarray. This is the part of Quicksort that I'm looking at right now. Our new pivot is now this 16. So I'll go ahead, I'll write those out, and now you'll notice that I've sorted those first three elements completely. Okay. So if I were to try and Quicksort, if I were to try and recurse again, go down another level, I only have one element, and one element is always sorted. You can't have an unsorted one element with itself. And so we can look back up one level. Our pivot is in the right place relative to the left and the right. Both the left and the right are wholly sorted because they're only one item. And so we've actually finished our little Quicksort run on all of these three. I'm going to keep moving that. Okay, so now we have the segment that we have just sorted. We have our two pivots in the middle from our earlier partition. And now what we just need to do is work on this right segment over here. So let's go ahead and do that, working on that right segment. So now I'm going to go ahead and do the same thing to the right side. So I pick a new pivot that is going to be my 74, and then 27, and then 27 is smaller, 38 is smaller, the pivot 74 goes in the middle, and 89 is larger. So now we're going to recurse again, and I'll do Quicksort on this side and Quicksort on that side. So let's start with the left first. 27 is the pivot, 38 is a single element, so that stays put. That goes back up. We have 74, which is just in the middle, and then we have 89, which is a single element, so we're done with Quicksort for all of these. And now we have our three chunks once more. We have the stuff that was smaller, that was just sorted. We have the stuff in the middle, which didn't need sorting because it was all the same. And we have the stuff on the right, which was just sorted as well because we just ran Quicksort on it. And that is the entire Quicksort algorithm. It's not actually very hard once you realize kind of the core intuition at play here. And there it all is. So now the trick for us is to actually look at the algorithm itself. So we have a similar structure here in our code to what we've been doing previously with the way I was moving my hands and setting my variables to chunk out different parts of the array. In this case, the code that you're going to see in this class will also use similar variables to point to where we're up to. We're going to have a pointer fg, which means the first item greater than the pivot, and fe, which is the first item equal to the pivot. So in this case, if our pivot is 26, where would my fe be? My pivot is 26, so where should my first equal to the pivot pointer be? You had it before.
26.
26, there we go. So that should be fe. And where should my first greater than the pivot pointer be? Where's the first item greater than the pivot?
Oh, is it also the 26? Or actually, was it the 38?
Where's the first item greater than the pivot in this array?
Oh, 26?
The pivot is 26. So where's the first one
not the
bigger
other.
than 26?
74.
74. So this is going to give us our three segments of the array. We have one segment that is everything from A, FG up until N. And we have our segment that is everything between FE and FG. And then we have our last segment that is everything from 0 to FE. Now, you'll notice here that I'm including the lower bound, but I've excluded that upper bound there. So let's double check if this works for our middle one. Everything from FE to FG, not including FG, that's fine. And everything from FG, including it, to N, So what I should probably be doing is notating that properly with an open interval to show that it's not including that element on the outer side. And having written it out like this should hopefully make looking at the algorithm itself when we formally write it a little bit clearer. So let's go and do that now. Let FE and FG be the boundaries of our sections, just like we had before. Create an invariant. This is just like we've done so far, and it's going to be pretty similar in form to the invariant that we've created for both our binary search and our linear search. So in this case, we want to know that the boundary markers haven't crossed over. So this is just like our boundary markers of low and high in binary search, and that they're within the bounds of the array. Then what we want to do is make statements about what are the values of the elements relative to the pivot. So everything in this chunk over here, in the small half, or in the small third, in the small chunk, should be less than the pivot. Everything in that chunk should be equal to the pivot, and everything in that chunk should be greater than the pivot. Let's look at what we've written. That's exactly the same thing, just notated with closed intervals instead. So the translation is both FE and FG are within inside the array bounds. Everything on the left is smaller than the pivot. Everything in the middle is equal to the pivot, and everything on the right is bigger. Now, Quicksort itself. So if you only have one item, return. You're in the base case. One item, there's no work to do, it's already sorted. Otherwise, we have the following structure. So pick a pivot. In this case, we're just going to pick the 0th element as our pivot because it's convenient. Now, run the partition function. I'm not going to tell you how to write the code to run partition, but just let's assume that we've already proved its correctness elsewhere. We'll look at partition after. And use the partition function to figure out, to swap the items around until they're partitioned, and to set the boundaries of FE and FG appropriately. Now we know by the definition of our invariant that if partition has been performed correctly, then this is necessarily true. So I haven't proved partition works yet, but I've just said let's assume we do have one that works. And if we do have one that works, this property R is definitely still true. Run Quicksort on the left, run Quicksort on the right, and then we have our post condition. So assert that everything in the small part is sorted. We know that it's sorted because Quicksort works. If we assume that Quicksort works, then we can say that that left half is sorted. Everything on the right side is also sorted by the same logic. And also we know that we're partitioned, so we have a global sort. Because everything to the left is sorted, and the middle section was bigger than the left. We know that everything on the right is sorted, and everything on the right is bigger than the middle. So sorted on the left, bigger, sorted on the right. The whole thing must be sorted. And that is combining our three properties. Now, you might say, well, how is this step valid where we've used the fact that Quicksort is sorting the left and using the fact that Quicksort is sorting the right? This is known in mathematics, what we've done, as a proof by induction. Because you'll notice that each time that we've run Quicksort, we're actually running it on a smaller version of the problem. And on top of that, on our last slide, we had a base case, which means if we can be guaranteed that the base case works, and we know that the composition is going to result in stepping forward that for like n+1 is going to be valid too, then we know that for n, when our problem is of size n, that is going to be valid as well. So that's almost the entire proof for Quicksort, much simpler than the others in some ways, except the fact that we actually need to define this partition function and need to prove its correctness in order for the overall proof to hold and for Quicksort to work. So partition is going to do this permutation that we've been talking about, creating the smaller, equal, and bigger sections. And it's going to return the new boundaries of those sections. So the basic idea is fairly simple. If the current element is small, put it on the left of the boundary and move the boundary right by 1. If the current element is big, put it on where the FG boundary is and move the FG boundary 1 more to include it. If the current element is equal to the pivot, you don't have to move the boundaries at all. You don't have to shift anything. So let's see this on our iPad in action with FE and FG. When we start off here, the first thing that we see is the pivot. And our condition for partition was if the current element is equal to the pivot, just continue. Okay, so continue. Look at the next element. We're now looking at our 16. Is 16 smaller than the pivot? Yes. So put it on the left of the FE boundary by doing a swap. So we're going to swap these two. So we'll get 16 and then 26. And then move the FE boundary up by 1 position. Okay, now we're looking at the next element along. It's 19. 19 is smaller than the pivot. And so what we're going to do is we're going to swap it. So do a swap with those positions. And that is going to result in writing 19 over here, 26 over here, and moving the boundary over 1 more. And so you can see that as we repeat this procedure, the first equal to the pivot is always being moved along to make sure that we're not breaking our property. So let's do this with 12 very quickly. 12 gets swapped along. FE gets moved to here, and 26. Now for the first time, we're about to hit 74, which is larger than the pivot. So now what we're going to do is we're going to do our other step. So let's look at what we wrote. We said if the current element is big, put it where the FG boundary currently is, and then move that FG boundary left. So what we can do is we can take our 74 and our 89 and swap them. So we'd put 89 there, 27, 38, 26, 18. And now we have 74 here, which was the one we've just looked at. And now move FG over 1. Okay, now the next item we look at is 89. Okay, 89 is bigger than the pivot, so do the same thing again. 18 and 89. And now FG needs to be moved 1 more along. So yeah, FG needs to be moved 1 more along, so I'm going to rewrite that in. And FG now includes everything to this side. And FE includes everything to that side, and as we go along, we're going to keep our invariant true this whole time. So let's finish off this run for partition, just so you can see the whole thing in action. So now we're at 18. 18 is smaller than the pivot, so we're going to swap it over. We're going to move FE. And now we're looking at 27. 27 is bigger, so we're going to swap it to the place where the FG boundary is. And then move the FG boundary along. Now we only have 1 item left for our partition, and that's our 38. 38 is bigger, but it's already in that position. So all we need to do is move our boundary along. Now you'll note something if you've been paying attention. This part is not yet sorted. That part is not yet sorted. This part is sorted, but that's just everything equal to the partition. Partition does not guarantee you that the left half will be sorted, that the right part will be sorted. What it does do is it establishes this ordering relative to the pivot. After you've done that ordering, you then need to run quicksort again on each of those halves to actually guarantee that they become sorted. So all the partition does is set up where the smaller things are, where the larger things are. It doesn't say that all the smaller things are in order from smallest to largest and that all the largest things are in order from smallest to largest. All it does is move them into place so that they're ready to have quicksort run on them. So now we can go back to our proof and we'll have an invariant for partition as well that looks very, very similar. So our invariant for partition is again that we have FG and FE are going to be within the bounds of the array, but we're also going to have an additional pointer, and that's our next pointer, and that's just going to point to the current element that we're looking at. Then what we have is everything to the left is smaller than the pivot, everything to the right is bigger than the pivot, everything in the middle is equal to the pivot, and on top of this, we have one more condition, which is that the pivot is either between the item that you're currently looking at and the first greater, or first equal is smaller than next. So this is another way of saying that the pivot is between next and the right boundary. So we have our initialization for pivot, we have our initialization for partition, which is just setting our boundaries up. So next is looking at the first element. We haven't set up a boundary yet for FE, so it's everything to the left of nothing. FG is on the far right-hand side, so there's nothing in there yet. So we know that P is already true because we currently don't have a possible way of violating it. Then we have a loop. And this loop is just what we did by hand. It's while you still have items that are not looked at, and we know that an item is not looked at if our pointer still hasn't reached the boundary of where we already have arranged things. So remember, everything on the far upper side is stuff that we've already looked at and swapped into place. And so if we hit that with the current item, then we know that, oh, we've already looked at those. We shouldn't actually keep going that way because we've already done the work to move those into place. So we can assert our invariant again because we haven't really changed much at this point, but we can also additionally assert that the loop condition is true at this point because we're inside the loop. Then, if the current item that we're looking at is less than the pivot, swap first equal with the one you're currently looking at, and then move first equal up one. So this is just saying swap that pivot over one and move the boundary. And when we've done that, we can assert the partition property again. And the reason we can assert the partition property is we know that this swap is going to ensure that that's true. Then we have our other case. Our other case is if the thing that we're currently looking at is greater than the pivot. So if it's greater than the pivot, swap it into that upper half, move the FG boundary down one, and then we're able to assert the partition invariant again. But we still have one more condition. What's our last condition, Melvin? So we have if it's smaller, if it's bigger, if it's neither of those, it must be
Equal.
Must be equal. So otherwise, we said you don't have to do anything if it's equal, just move on to the next element. And so in that case, we can assert our partition invariant again and keep saying that we're still within the first equal is still less than next because we've just incremented next, so that can't possibly have violated it. So when the loop ends, we now know that next must be bigger than FG because that's how the loop ends. The loop ends when next crosses over that FG boundary and becomes equal to it. We know that P is still true. And we also know that first equal is less than next. And so let's look at it from our iPad. We're saying that the partition property is true, which it isn't what we've done. Next is now over here. This would have been the next element, but we're not going to do anything with it because we're out of the loop now. And also FE is less than next. And these are all the things we need to overall say that the partition algorithm is correct overall. So let's put it together. We had our quicksort algorithm, which was correct, so long as our partition algorithm was correct. We have now just proven the correctness of partition, and so we now have a complete proof for the correctness of quicksort. And this is probably the most difficult formal-ish proof that you will see in the semester. But we still have a little bit of work to do on partition. We haven't talked about its efficiency yet. So this proof is a little bit tricky again, so don't worry if you don't follow all of it. So the way it works is set up a variable t and set this variable t to be the difference between fg and next. So this is essentially saying how many more items do you have to look through? Because once next is equal to fg, the loop ends. So fg is over here, we're slowly making it bigger, and these are the items we're looking at. And when we have looked at all the items, we've hit that boundary. So let t be the gap between fg and where we're up to. That's just how many items we have left. So at the very, very start of the algorithm, fg is at the far side on the right, and next is the very first item. So at the very beginning, we know that t0 is n, because you've got n items to look at, you've made 0 progress so far, and so the gap between what you've got left to go and where you're starting is n items. Now, every time, if you look at the partition function, you're either moving up to the next item, or you're moving that fg boundary down 1. And so if every time you're either moving that up 1 or you're moving that down 1, the distance between them is reducing by 1 every single time of the loop. So every time the loop runs, you're either pushing that up or you're pushing that down, so the gap must be shrinking by 1 each time. The loop ends when there's no gap between them, because they've hit, and that was the condition of the loop n. That was the condition at which the loop ends, and therefore this must be an O of n function. Why? Because there are n possible things, you know, that goes 1, 1, 1, 1, 1, 1, 1. You can only do that n times before the gap goes from n to 0. So I'll repeat that once more. T starts at n. Every time the loop runs, t gets reduced by 1. How many times can you go from n to how many times can you subtract 1 from n before you get to 0? N times. So that is O of n. What about quicksort itself? So you'll remember quicksort had a base case with just one step. It had then partition, which is O of n, and it had 2 recursive calls, each of which worked on at most half of the initial size of the array. So we can write it this way. Do n work, which is for partition, plus do 2 recursive calls, and each of those recursive calls are going to take half as much work as it could have taken for you to do that whole amount of work at your for your full n-sized array. In the best case, when we do partition, we're going to end up with equal-sized halves to send off to the recursive calls for quicksort. So in our best case, we get the recursion relationship as follows, which if you're in the more comfortable tutorials, you can do a proof that takes you to n log n runtime. So that's our best case. In our worst case, we end up with, we've picked the worst possible pivot every time, and actually there's nothing on the smaller side of the partition. What we get is we get the pivot, and then everything is greater, and then we have to run quicksort again. And then we pick the worst possible pivot again, and so we've only got one item to the side, and then we have to run quicksort again on everything else. And if you sum up how much work you do in that case, you'd get O of n squared. And so you actually get a different recursion relationship based on how effective your partition is going to be on the input data set. And so quicksort is still worst case n squared, but we will talk about average case in a moment. But for now, I'm going to show you Quicksort in C. So let's look at our Quicksort function. It's actually really simple. So the first thing to do is to choose a pivot, set up first equal and first greater. Then we have our base case. If n is less than or equal to 1, so if there's only one element in the array, return. Otherwise, choose a pivot, partition, and then quicksort on the left, quicksort on the right. Now you'll notice a couple of things here. In order for partition to be able to modify first equal, first greater, and what our pivot will be, what we're actually doing is we're passing the address of those variables so that the partition function can modify them and the changes will still be reflected in Quicksort itself. The other thing you'll notice here is I'm using data_t. Now this is a type that you haven't seen before, but our program is using a feature of C that we haven't seen yet in the class. Let's look up over here and I have a new keyword. This is typedef. It allows us to make our own type. And in this case, the type that I want to make, I'm going to create a type called data_t, and I'm going to make it really simple. In this case, data_t is going to be exactly the same as an int. So the syntax is on the right, I'm going to put what I want to call my type, and it's pretty typical in C to to call a type that you've made yourself, something _t so that everyone knows it's a type. And then on the left-hand side, you have the description of the type that you want it to reflect. So in this case, the type that it's reflecting is a really simple one, but we'll see in later weeks how we can make more complicated custom types in C. So for now, data_t is just going to be the same as an integer. The useful thing here, though, is let's say that I wanted to sort floats. All I would have to do to make my code work with floats is I could change this to float or double, and automatically all the types in my program that refer to a data_t would change to really be referring to a double. Now let's look at partition. Partition sets up our pointers. It starts next and first equal at the far left-hand side, first greater at the right-hand side, and then creates another temporary variable that's just going to be used in here called outcome. Now, notice that in the type signature here, our pivot, first equal, and first greater are all pointers. We want to do this so that we can change what they're pointing to inside here. Next up, we have our loop. And this is ensuring that we're always looking at the next item until we cross that boundary. And now what I want to do is compare the two items that I'm supposed to be looking at. The item that is at the start of the array plus next and the pivot. Now, one thing that's really weird here is A is my array, but I seem to be adding to it. Now, this is a functionality of arrays that we haven't really talked about. Because an array is really just a location in memory, an array is really a pointer to a location. And so if we do mathematical or numerical operations on it, what we can do is jump to different places in the array based on how much addition we've done. So A plus 3 would be moving 3 places on in the array. And the compiler is smart enough to know that if the array is a char type array, each of those additions will be one char worth in memory, which is 8 bits, which is 1 byte. That's correct. But if it's an int, and I do an int pointer plus 1, it's going to move us 4 bytes along, or 8 bytes if we're on a 64-bit machine. Now, the reason that my program is doing it this way is so that we don't have to worry in particular about what type we're using. We want it to be what we call polymorphic. We want the same code to work with lots of different types. Polymorph is Greek for many types, and so we want my code to work in theory with many types. And all I have to do is write a function called CMP that works for comparing those types. So let me jump to my CMP function. And my CMP function is actually going to be defined in a different file. And so this leads me to another part of my code. I have this new directive. We've seen include before, but I am instead including something in quotation marks, sort scaffold.c. And the quotations are going to indicate that it should look for it locally here where my code is. And so let's open up this sort scaffold.c. And what include is going to do is it's actually going to bring all the code in sort scaffold.c into this program itself. And so I can look and see what the CMP function does. And this is a very common pattern in C to have these CMP functions. And what a CMP function is supposed to do is it's supposed to take in 2 pointers of a particular data type and then tell you which one is bigger than the other. And the way you can tell which is bigger between 2 items is by subtracting one from the other and seeing if you get a positive number, a negative number, or a 0. So that's what our partition function is doing over here. We're setting our outcome to either be positive, negative, or 0, depending on the relationship, the size relationship between the next element that we want to look at in the array, so that's the array plus next steps, and where the pivot is up to in the array. And so we have the case if, I think this is if next is less than the pivot. So in this case, we do the swap of the first equal one and the next one, and we move the equal boundary along, and we move to the next item. We have the case if the item was bigger, in which case we move the first greater boundary down a little and we do our swap, and otherwise we're equal to the pivot and we just move to the next item. You'll also see here that I'm using an assert statement. You can actually write these asserts into your C code and the program will crash if they don't happen to be true. Then what do we do at the end? I am going to use the dereference operator to set back in the main quicksort that was calling this partition function where the new boundary should be located for first equal and the new boundary for first greater than. So now we're left with one kind of interesting question, which is what pivot should I choose? Up until now, just been saying, well, let's not worry about it. Let's pick the very first element. But what the code that I've written is going to enable us to do is actually experimentally test how well do different choices of pivot work. So in this code, I have 3 different versions. I have some code which returns a random pivot, some code which returns the midpoint as the pivot, and some code which just returns the very first element of the pivot. So which do you think is going to be best? Hands on head for random, hands on shoulders for midpoint, hands in the air for the first element. A random, midpoint, first element. Okay, let's test it and find out. And we'll then talk a little bit. Actually, I'll say that now. So the way that we can create a random number in C is using this rand function. And then the modulo operator is going to tell us how big that random number is. So we can bound it by n by using the modulo operator to make sure we don't go outside a certain bound. I will say this is not going to give you a uniform distribution necessarily. And there are other tricks and traps for using random numbers that we'll talk about a little later. But for now, let's run quicksort.c with a random item as the pivot. Oh, it's not called quicksort, it's called a.out. So this was with our random pivot. If we're looking at items that are already sorted, we get 20 comparisons per item, 60 copies. For reverse sorted items, we get roughly the same thing again. For items that are all the same, we only get 1 comparison per item. And for random items, we get 20 comparisons per item. Okay, let's comment this line out and run it again. Oh. Okay, this looks like it did better on sorted and reverse sorted. Did the same on uniform. And what about random items? This was 20 copies per item. This was 20 copies per item. $827, $828, $829. Class is just about over. So we can clearly see the loser in this case. Now let's try it with the midpoint one last time. There we go. So we do slightly better on sorted and reverse sorted. Random turns out to be roughly the same. Turns out in practice, we typically choose a random pivot. We do not choose the 0th item as our pivot. That turns out in practice to be the wrong choice. Okay, so what about on the average case? How do we figure that out for Quicksort? Does anyone know how to figure out the average case for Quicksort? I would be very impressed. It's quite hard maths. And if you go on Stack Overflow, you can see some of the nice proofs, or maybe these days you ask ChatGPT instead. So one way you can think about it is you could imagine that the array is a random permutation of what would have been the sorted array. And then the first item is also going to be random, and so we could use it for our pivot. But this is going to rely on the input data being random. We could imagine it this way, that we could imagine that the first item of our array is random if the array actually ends up being random. But often, arrays are not entirely random. And so if the array comes sorted or reverse sorted, then choosing our first item results, and then choosing the first item as the pivot is going to be the worst case for us. We get that behavior where you got that n squared. So instead, what we can do is we can alter our choice of pivot so that we don't end up in these worst case scenarios if we're dealing with sorted or reversed sorted pivots. If we choose the midpoint as the pivot, this becomes very hard to analyze mathematically. There is a way of doing it, but it's very hard to do. Other plausible choices is choose the median of the start, the middle, and the end. But in practice, it's going to make our analysis much easier if we end up choosing a random element. Then what we do is we construct this fancy little sum. We can figure out the expectation value of the runtime. So we sum over all the possible different splits that it could end up. And we can do this because now we're choosing a random pivot. And so if you use a little more advanced maths, we eventually get this average case runtime. 1.44 n log base 2 n plus O of n, which is n log n. And so we actually end up with an average case n log n sorting algorithm, which is better than the other algorithms that we've seen so far. And now the input sequence doesn't actually make a difference for our analysis. The expected running time is always going to be big O of n log n. But this leaves us with an open question. Is it possible to do sorting in worst case, big O of n log n? And let's revisit that question later in semester. Thank you very much and have a wonderful night.